And then I will call up my PowerPoint. Oh, I can't call up my PowerPoint directly. I got to do this. Okay, close. We talked about all that stuff. We were looking at circuits. So the thing we don't know completely what to, oh, I'm not sharing my screen, am I? Where's Zoom? Share screen. I am recording though. That's amazing. Okay, so the thing we don't know what to do with yet completely is that capacitor. Part of the answer is I replace it with a capacitor of 1 over SC. But that's only one piece of the answer. Get up now and leave it. Okay, we'll get to that. So we got to figure out what to do with the capacitors and the inductors. Okay, and I really went through and rewrote these slides this morning. I actually have time to do that now. Okay. Remember the voltage sources, they just get transformed. We take the Laplace transform of whatever their function is, and we put that in the S domain. Same thing with current sources. Ohm's law works in the time domain. It's also going to work in the frequency domain. Now, the way we get to capacitors and inductors is we start with a basic equation for an inductor. So V of t is L di dt. And I go over to my little Laplace worksheet. I'll get it out. And what I find is the Laplace transform of the derivative of a function in t is simply s times the undifferentiated function. So I just take f of t and find its f of s, multiply by s, and I don't have to take the derivative. But there's another little term out here, minus, and this is little f of 0 minus. So that's the initial condition in the time domain. This is in the time domain. So if I have an initial energy stored on that capacitor or that inductor, I'm going to have to model that somehow. So I start out with V of t's L di dt, and I transform that to V of s. Well, I've got the L out front, so I got to multiply the whole thing by L. And then I've got to multiply the function I'm taking the derivative of by s. I'm taking the derivative of I, so that becomes I of s, and subtract off I of 0 minus. And I can use a little bit of algebra, and I can flip that around and solve for an expression for the current in terms of V of s. Now, okay, we'll get to that when we start looking at circuits. I of t is C dV dt, which I started out doing this one. This is the one I actually did first. I of s would be C dV t dV of t dt. Thank you. I multiply by s, and then I have V of s in there. I just transform that V term and then subtract off little v of 0. So that's in the time domain. And then I do some algebra and flip it around, and I solve that equation for V of s, and I come up with this. So there's an extra term in here. It's not just SL and 1 over SC. And we'll get to pictures in the next slide, which is the part that I like. Okay, if I have an inductor in the time domain, I have something that looks like this. And I put the equations on these slides too to make them make more sense. I of S, let's start out with the easy one. V of S, I'm modeling as two pieces. One is SL I of S. So this is like an inductor with an impedance value of SL, takes care of this first term. Then I need to add in a voltage source that has a value of L times I of 0 minus, pointing in the wrong direction. So if an inductor has energy stored in it at time t equals 0, I have to add that little voltage source in. Not that I've ever done this very often in my life. Usually what I define as t equals 0 is when I push the button and turn the power on, which means there's no energy stored in it. Now we use the other equation, this I of S equation. Again, I end up with something that looks like Ohm's law, and I get this inductor that has a value of SL. I can also model that. I can model this other part as a current source, I of 0 minus over S, and it's going in the right direction because now it's positive. If you look at these two circuits and remember source transformations from EE280, one is just the source transformation of the other. So it's not something you really have to memorize. And I tend not to put circuits that have initial conditions on the exam because I never, okay, but it shows up in some of, I don't even know if it shows up in the homework. I would have to look and see. But it will show up in some of the slide problems. So for a capacitor, here I've got my simple one is over here. Okay, so normally in the time domain, I have a capacitor, passive sign convention, currents going into the positive terminal. I'm going to have to model that as an impedance 1 over SC. And now that initial condition is represented by, it's got a minus sign, so it's going in the wrong direction. It has a value of CV of 0 minus. I could do a source transformation on that or use this equation. And I could also model that capacitor as 1 over SC with a series voltage source. Which one of these do I pick? If I have a circuit where everything's in parallel, I'm gonna use the parallel model. If I have a circuit where everything's in series, I'm gonna use the series model. It doesn't matter which one you pick because they're just source transformations of each other. And you can make your analysis simpler if you simply pick the one that's most like the circuit that you're using. Okay. I told somebody I was going to talk about op amps today. I did not write the op amp module in 188. I taught it and added my own slides. Other people may have copied. So I don't know what you've learned. It was a very Dr. Brower-ish looking thing. Okay, these are the next. All the stuff on op amps are stuff I've added since I've been teaching this course. Now, op amps are often, you'll often hear me refer to them as the magic triangle. And we'll talk about op amp design, the design of a diff amp in EE280. And if you want to learn how to use op amps, 490 in the fall is probably your best bet, along with anything to do with printed circuit board design or general analog techniques. So the first rule that I have here is what I do is I make this ideal model and I say that I have an infinite resistance between these two terminals. So this Rn is infinity. Infinity seems like a big number for a resistance, but you can easily find op amps that have an input resistance of a teraohm. 100 megohms is not uncommon. Gigaohms is not uncommon. But if you really want a good one with a high input, or you really need a high input resistance, a teraohm is out there. So this is actually a pretty good approximation of reality. We'll talk about when it's not so good somewhat in 490. If that's true, this resistor is big enough, you can't drop any voltage across it, then V plus equals V minus. The first thing I do when I look at an op-amp circuit for the first time is I assume the voltage on the positive input is going to equal the voltage on the negative input. And then I start worrying about the fine details later, like when I simulate it. I let multisim handle the simulation at this point. The other thing is, since this resistance is so big, if I drove a current into it, I would have a huge voltage drop pretty quickly. So there's almost no current going into either one of those terminals. So the current going into the plus terminal is 0. The current going into the minus terminal is also 0. In reality, that current may be picoamps. It may be nanoamps. Just depends upon how good of an op-amp you have and what you need for your application. The difference between these two terminals, it is specified on the data sheet. We're not responsible for this class, but this is for the people who don't take 490. It's called B offset. And my favorite op-amp that I've been using a lot lately has an offset of 25 microvolts. Millivolts is not uncommon. Okay. For an ideal op-amp, and we'll talk about this more in 382, why this is a good thing. One of the 10 essential skills for electrical engineers. You'll get this in 380. The input resistance is infinite, which is great. The output resistance is 0. It's really more like 50, 100 ohms or something like that. And the gain is infinite. So this is, real numbers are like 100 ohms, maybe like gigaohms here. And the gain may be 1,000,000 easily. So these are pretty good approximations, and it's what I use every time I'm looking at an op-amp circuit for the first time, or I'm trying to figure out how to build one. The output voltage can be anything, but it can't be bigger than the voltage I put in. So the voltages I put in are these power supply voltages. It's limited by VS plus and VS minus, the power supply voltages. In reality, the best, and I would know I was looking for this recently, the best rail-to-rail op-amp I can find will only get you to 100 millivolts of the positive power supply and 100 millivolts of the negative power supply. And that's what they call rail-to-rail. I know, because my grad students, not really my grad students, the grad students I work with insist that they think they can go all the way up to the top, and they never even look at that. And you'll be looking at it and go, okay, you've only got a 2.5 volt power supply here, but you're expecting to get 5 volts out. That's not going to happen. Okay. Bandwidth is a new concept you didn't get to in 188, but that is where the frequency response starts to roll off. All of these op-amps act like low-pass filters. They have Bode plots that look like this, and they're designed to look like that. And this is what we call the bandwidth. They will amplify down to DC, but there is a certain bandwidth that they will not amplify past. and their gain starts to fall off after that.
Could you briefly explain the VS positive and the VS negative again?
Okay, so the VS positive is the positive power supply. I'm not going to be able to get a voltage at the output that if I have an op amp and I'm running it from 0 to 2.5 volts is my power supply. So I'm running it from a 2.5 volts power supply and it's referenced to ground. I cannot get a voltage out of it probably greater than 2.4 volts. And the real kicker is I cannot get a voltage out of it less than 100 millivolts. So if I want good linearity, we'll talk about this a lot more later on. If I want good linearity, getting close to these limits is a bad idea. The circuit doesn't perform as well when I get really close to those power supplies. Okay. More of that later on in this class, 380 and 490 in the fall. Okay. This is an inverting op amp circuit. You saw it in 188, but the math probably confused the heck out of you at that point. It's fairly simple. This is a standard circuit. This is a formula I had memorized even as a working engineer. Somebody would ask me, you know, what's the gain of an inverting op amp? Minus ZF over ZS. But how you get there is basically applying these golden rules. We know the voltage at these two terminals has to be the same. This is golden rule number 1. This one's grounded, so this one must also be at 0 volts. I could have a power supply there, but in this case, it's 0 volts. Then I know the current going into the op amp is 0, which means that whenever I do KCL here at this node, all the current going into that node has to equal the current going out. So the one labeled IN has to equal I out. This is just like node voltage method. IN is going to be VN minus 0 over ZN. This could be a resistor network, it could be an RC network, it could be anything. But whatever it is, that's the current going in. The current going out, you got to be careful of passive sign convention because this one's going to give you a negative sign. I got the current defined this way. So the current going out is going to be, this would be the positive terminal and this would be the negative, would be 0 minus V out over ZF. And I do a little bit of algebra and I come up with the basic gain equation. And I have this one memorized. I gave it to you on the homework and I'll give it to you on the exam. So how can we use this? If ZF and ZI were just resistors, then this would reduce to negative the feedback resistor over the input resistor. And you can easily set the gain of your circuit just by choosing 2 resistor values. An amazing thing, op amps are really reliable. Very few people build single transistor amplifiers on a board unless they've got some kind of weird power supply constraints or things like that, or some frequency constraints that they can't get with an op amp. These are the workhorse of analog electronics as a starting point. Okay, there's a lot more to analog than what I'm able to teach here. First order low pass filter. So I can use the same circuit. It's just an inverting op amp. In this case, my ZF is the parallel combination of this capacitor and resistor. My ZN's what's hanging off the negative terminal. It is just a resistor. The feedback impedance is the impedance between the negative input and the output. And you always put the feedback network on the negative input. If you make the mistake and flip the terminals, what you've done is you've just created a positive feedback amplifier which is by its nature is unstable. You've built an oscillator by flipping those two terminals. So be careful with that one thing. That's important. Okay, so I've got a formula here for the gain. All I have to do is figure out what the pieces are. So Zn as a function of S is just R1. The feedback from the negative to the output is the parallel combination of ZC and ZR2. So I do product over sum. I get this messy fraction, 1 over SC R2 divided by 1 over SC plus R2. I immediately get rid of the improper fraction part by multiplying by these denominators. I'm just going to multiply that whole fraction by SC over SC. That's just like multiplying by 1. And when I do that, my SC cancels out in the numerator. I get R2, and it cancels out in the denominator, and I get 1 plus SC R2. So there's the transfer function. The transfer function. I have to take this whole thing for ZF and divide by R1. So I'm factoring out the R2 in the denominator. Now we got something that looks like those Bode plots we've been doing. A relatively simple Bode plot, but it's like the most common Bode plot you will ever see. This R2 over R1, I'm going to ignore the negative sign for now. The R2 over R1 is the gain. My K is R2 over R1. And it looks like I could put this into standard form. People, the first time you see this, they hate this, but basically what I do to put it in standard form, I don't have to divide by anything. I just take this R2C and make it divided by 1 over R2C. So my pole's not at the RC time constant, it's at 1 over that. So I've got a pole at omega equals 1 over R2C. That's a really common mistake. And I've got a DC gain. The DC gain was really negative. I do have to take account of it someplace. With AC signals, if you take a cosine and then you take the negative of the cosine, it's the same thing as shifting a cosine by 180 degrees. So the way that it usually ends up in the transfer functions is R2 over R1 with 180 degree phase shift. So that would affect the phase plot and not the magnitude plot. I've got the DC gain, I've got omega naught. I could plot this, and what this would look like was this point here would be 20 log of K, which is R2 over R1, would start out here. And this point, and the way you read these plots, whenever I get 3 dB down from that point, so this would be like right about there. Did I freeze? Yes, I froze. Okay, so when I get 3 dB down, 20 log of R2 minus R1 minus 3 dB, at whatever frequency that is, that it's really starting to roll off good, that is our omega naught, and that would be on the omega axis 1 over R2C. Okay, we'll come back with a design example.